Okay, so let's consider one of these three representations for the electric field at point A. We will most likely consider this one, the sum of the electric fields in the x and the sum of the electric fields in the y, because each of these vectors can be decomposed. Now, if we consider that definition, we see that the sum of the electric fields in the x is equal to the electric field of charge 1 in the x plus the electric field of charge 2 in the x. And we recognize that these two vector components are pointing in opposing directions, so they're going to subtract. So to change this sign to a minus sign, bearing in mind I am subtracting their magnitudes here to get the magnitude of the net electric field in the x direction. Okay, now let's do some geometry here with the picture. We see that I can define this angle theta over here, and this forms a 90-degree angle. Now we see that one side length is a, the other side length is 2a, because that is what a plus a is. And then if this is a right triangle, we see the magnitude of the electric field due to charge 1 at point 1 will be defined by this distance r1, and we see this is basically going to equal well, let's do the Pythagorean theorem to figure this out. We see that r1 squared must equal a squared plus 2a squared. So that's all in all is going to equal to a squared plus 4a squared, which is 5a squared. So we then see that r1 must equal to a times the square root of 5. Okay, so that's that distance. Now that we know that distance, let's recollect that this is basically a symmetrical picture. So R2, which is this leg of this right triangle, that hypotenuse of this right triangle also has the legs of A and 2A. So this angle must also be the same, theta. So therefore, R2 is equal to A times the square root of 5. So R1 is equal to R2. So now we know what those two side lengths are. So just gonna write this a bit nicer. Okay, so now that we've established that geometry, let's go ahead and figure out what the x components here are for each of these vectors. So it's not so bad. If you take the EY components of both of these vectors and translate them over, let's say for E2, you move it here. And for E1, you move the y component here. What you see is more right triangles. Nothing new, nothing fancy, nothing crazy. Now, you can then recognize, where does that angle theta that we defined earlier show up again? It shows up over here. There's theta, right? Therefore, what else can you say is theta? Well, corresponding interior angles. So you see that this must be theta. Likewise, if we consider theta for the second charge, this theta will show up here, alternating interior angles, and then corresponding interior angles. There's theta again. And now we see that we fully define this geometry in terms of theta. Okay, so we can get what the x components are, as well as the y components for each of these guys. So let's continue this in another video.